Right. Okay. Good morning, everyone. Let's try that again. Okay. So this is a very good question. Let's say we have this feed, and the feed just really straight line go to the to here. So is it should be in stage 4 or stage 5? Yeah. Uh, Rosemary argue it should be in stage 4 because it's in the feet of the triangle, let's say, yeah. Um, or but Pak Udin may argue that Bu, that it should be similar to this one, ya, to the stage 5, ya. Harusnya kan sama di sini gitu. Kenapa dia nggak bisa ke sini gitu ya? So, in order to explain the graph, is this much better if you combine them with wait, I'll use my yeah, okay, yeah, it's gonna be used if I can use a sketch, yeah. Pen. So this one, okay, let's say this is the stage 4. Yeah, what happened in stage 4? So this point, yeah, this point is the composition of the stage 4. So this point, the axis is actually equal to x4, yeah, and also y4. Okay, yeah. Now because we have the feed and the feed is saturated liquid. The feed is saturated liquid. So with the composition of X4 there, so it is better if we put it all in. What happened, the feed for saturated liquid is perfectly fine to be put in here. So this is going to be the feed. Okay, that's why it should be in stage 4 because the composition is the same. Okay, now what happened? If the feed is if we put in stage 5, what happened if we put in stage 5, then because the stage 5, the composition is this one, yeah, the composition is this one. So let's say this is their stage 5 there. So what happened is and the composition for the liquid is this one, yeah, in the stage 5, right? So it may not be optimal, and the feed there, the saturated liquid, will be maybe flash. It's like flash vaporize some of them, yeah. So if we want to put at the stage 5, we have to have a better Q. Yeah, we have to have the Q around this area, so that means maybe a part of them should be vaporized. Yeah, so a part of them should be vaporized. Okay, yeah, so that's good. So I hope you, if you have a doubt about where to put or where to put into the graph, please make this stage, yeah, make the stage, and then the sketch of the stage, and also so every point will show you the correlation. Yeah, this point in the equilibrium will show you about the equilibrium. This point in the feed will show you about the correlation between the operating line between the x, yeah, the stream that is parallel, yeah, which is in counter current. For example, between the Y5 and X4. Okay, yeah. Hopefully that's this is our discussion this morning with the lecturers.
Yeah, because that's their assignment too.
Oh yeah. Okay.
Okay. Okay, some of you might have find that your feet is enter the column in the fourth stage. I think I have your answer here with me. Later on, we will discuss about it. Maybe
Okay.
at the last 20 minutes. Yeah.
Okay, yeah. I think, yeah,
So
for book
please
grades, maybe
continue.
around 11, yeah, 11:20 or 11:15. Okay,
Okay.
okay. Thank you, book grades. Okay. So now we're gonna just move on up to here. Oh, yeah. Okay, so yesterday we talked about condenser. Yeah, this one about partial condenser. Again, there is several type of partial condenser: the partial condenser, total condenser, and this one. So this one also I took from the book of Seder. There is three types of condenser. The first one is the total condenser. So in this case, all of the just put it. So in this condenser, all of the vapor there, all the vapor is cooled down into a liquid. Yeah, and in the liquid there is going to be a drum. Yeah, and where this drum and would be, there is maybe a valve over here, so they can control the ratio that the liquid going back to the column and also the distillate. And this one, yeah, this one is the reflux ratio. Yeah. The second one is a partial condenser. For partial condenser, you do have one stage of equilibrium. Yeah, one stage of equilibrium where the product is we gonna get the product as a distillate, as a small as a vapor fraction there, and the liquid, all of the liquid is turned back into the to the column. The third one, mixed condenser, where we're gonna get similar to the partial condenser, the vapor distillate, but not all of the liquid going back into the column. So some of them is also took as a liquid distillate. Yeah. For this case, the vapor distillate and liquid distillate will have different concentration based from the equilibrium. Yeah, but a vapor distillate and liquid distillate is in equilibrium. Okay, so this is also yeah, a schematic. Wait for me. Wait. Yeah. Sorry. Because everyone just like apa, teriak-teriak ya. Okay, all right. Now, this is also example. I always gonna repeat it again and repeat it again. For a case of partial condenser, this is gonna be your, this point, yeah, this is gonna be your YD over there, which is the mole fraction of the vapor, and the X, the reflux that going back there is this one, yeah, this point. Okay, so for for a schematic like this is gonna be the partial condenser, and this is your stage one. Yeah, this is gonna be your stage one over there. Okay, and also for partial reboiler, it's also similar. So this one is the XB and YB. So partial reboiler looks like there. Yeah. Yeah. So this one is going to be the bottom, the XB, which is this one, yeah. And the YB, which is the vapor that going back into the column, is this one. Okay, so this is going to be one stage as well, one stage of equilibrium. Okay. A total condenser is recommended for a reflux drum pressure up to 14.8 megapascal, or that would be about, yeah, this is very high for this one. A partial condenser is appropriate from 14.8. A partial condenser also can be used below that one. So this is actually just like a rule of thumb. Would be beneficial if you want to design the this distillation column in your group assignment later on. Yeah, mixed condenser also can both provide both a vapor and liquid distillate. Now, okay. Now today, let's talk about what is the difference between partial and total reboiler. Yeah. This is the schematic of partial reboiler. Yeah, in partial reboiler, that means you have one stage equilibrium there. Yeah, so this one is your reboiler. Yeah, this point is your reboiler between the, let's say for this one is XM, and also the YQ is the vapor phase that going back into the column. Okay, so if I want to ask you, for example, this is stage N, what is the composition, what is the composition of stage N there? So that means you have to know the V, yeah, the V, sorry, the liquid L dash, and then this is the composition of this one. How you get the composition of this one? The X from, is it from the operating line, yeah, from the stripping operating line. So this one, yeah. So this one is gonna be your XN. Okay. Yeah, so this, if this is the stage, if this is stage N, your XN is in the stripping operating line. Okay. Now, okay, so this is the XN. So how to get YN? How to get YN? Then you can see this point, the point which is the equilibrium point. This gonna be the YN and YN and XN. Or for this case, the YN is XP. Yeah, so I'm just gonna put YN. Okay. How about okay? How about partial reboiler? What happened in the partial reboiler? The second one is this one is sorry. This is a total. What happened with this one? Kayaknya ada ini. I'm sorry, my why this is happening? Okay, so this one is total reboiler. Total reboiler. In total reboiler here, you actually pick up some of the XB, yeah, and also all of the XB is all vaporized into the vapor phase. Yeah, so this is total reboiler. Okay, This is also the type of reboiler. You may gonna use it later on when you use HYSYS, because when you're using HYSYS, there would be a type of reboiler that you need, and this would gonna be helpful for the heat duty, heat duty uh, of the condenser. Sorry, of the reboiler. Yeah, this is a typical. The first one is typical a kettle type reboiler. This one is a thermosiphon type reboiler, where the reboiler liquid drawn from the bottom sump. This one there. And then the third one is a type of vertical reboiler, thermosiphon type, where the reboiler is drawn from the bottom tray of downcomber there as well. Yeah. I think this one should be the same. The vertical type, the bottom sump and bottom sump and bottom tray downcomber. Yeah. The difference is the this one. Yeah. The type of the inlet that used for the heat exchanger. Number C is based from here, and the bottom tray there. For here is from the bottom sump there. Okay, now one more, yeah. Before I talk about the heat duty, one more is sometimes in some of the distillation column, sometimes we inject just steam, yeah. If the XB is, for example, a typical of acetone with water, let's say. So rather than we heat it up the acetone, we just inject the steam, which is steam also H2O, yeah, steam. So what happened in here? So to get, we need to find the point, yeah, the point in here. What happened if we inject the steam? So the liquid will have XB, right? It will have XB for the composition. So the XB composition, so this is the composition of the liquid. Now, the composition of the steam. What is the vapor composition of the steam? The vapor fraction of the steam. Because the steam is, let's say there is a two component A and B, and for example X is the liquid fraction of A, yeah, and Y is the vapor fraction of A. For the steam, there is no vapor fraction of A, right? There is no A in the steam, so that means the vapor fraction of A is 0. That means Y also 0. Yeah, so a pair of XB and Y, that will become XB comma 0. Yeah, so the Y is 0. That's why the point will the point of, instead of in here, the point of the XB there, for the operating line for the stripping section, would be in this point. So then when you and then you have over here is the, maybe for example cross section between the key line and also the enriching section. So from that point, draw the line to the XB, the XB point there, then you're gonna get a stripping line. Up to here, any question? No? So that means that would be a lot of configuration. The condenser can be total condenser or maybe partial condenser, yeah. The reboiler may be partial reboiler, usually is partial reboiler, but maybe total reboiler as well. And also for reboiler, there's another one, which is yeah, this one, open steam. Yeah, so you need to know the where to put the point, where to calculate the points. Okay. Okay, any questions? No? If there's no question, I'm gonna talk about heat duty. Yeah, the heat duty is usually the last number. So I would say in exam of distillation, there would be one problem for the first problem, and it usually will have anak-anaknya ya, maybe around 12 sub problems, sub questions, yeah. And usually the last question is this one, the heat duty. And sometimes students is not passing this one. I don't know, it's because of they just forget the mass balance or energy balance, or I don't know. But this is actually basically from mass balance and energy balance. That's why I think in the class it's not really it's really explained well. But maybe in the tutorial, yeah, we need to do like more hands-on about the heat duty. Okay, the heat duty, condenser, and reboiler is actually how to calculate the QC, which is the heat duty, yeah, for the condenser, and also QB for the reboiler, right? For the idea, so the basic idea is all about mass balance and energy balance. Yeah, about mass balance and also energy balance. So here, can you tell me what is the mass balance in the condenser?
HV equals HD plus HL.
The mass balance.
Oh, V times HV
That's in energy balance. That's right. V times HV.
equals to
Mm-hmm.
D times HD plus L times HL.
D, okay, plus
L
L,
plus H.
and then the balance is we need to add QC as well, yeah, and also the end of the Q. Okay, so this is the balance. This is the for energy balance, and for the mass balance would be V equal to L plus D, right? Is it?
Yes.
Yeah,
Yeah.
yeah. So the idea is the vapor um uh should be withdrawn the heat, yeah, the energy inside the vapor by we putting heat duty of the condenser using uh, cooling water, for example, and then the remaining enthalpy or the remaining energy is in the distillate and also in the liquid. Okay, for the reboiler, so it's also the same. So for this case, it's equal to the L equal to C plus B. Yeah, for the mass, and also we need to add, so and for the humidity for reboiler, that means L and HL and LL, and we also need to have to add, if we add the Q reboiler, should be equal to VHP plus BHB. Okay. Yeah, so this is the heat duty of, so this is the idea. So I would think you need to see the phenomena again, see what the schematic of this one, and then you can construct your mass balance and energy balance. However, if you think you just forgot the idea or yeah, something like that, you can ask the assistant, or we can get some tutorial. Yeah, next week we still have some more time next week, because actually I'm actually much faster compared to regular class. So we still have 1 week next week to add more exercise. Yeah. Okay. So I would say this is the energy balance. So the entire column. This is for the entire column, and this then if from the feed, yeah, from the feed. So the enthalpy in the feed multiply with the feed rate plus the reboiler. So because we add the reboiler, it would be equal to the distillate and also the bottom at the bottom there, and also the Q that we withdraw, which is the condenser, and also some kilos. Yeah. So the energy balance for total condenser is this one. We have the Q condenser based from this one there, yeah, and the Q condenser is actually the V multiply with the this one, yeah, sorry, this is we got this one already, and then maybe we put R reflux ratio there equal to L over D. uh, with that, then especially it will give this one. So we need to know the average molar. What is average? Average is basically we add it if we have XA, yeah, or sorry, for the vapor maybe YA. It's basically the enthalpy separation average would be the YA multiply with enthalpy of vaporization of A plus YB actually, yeah, or 1 minus YA multiply with the enthalpy vaporization of B. So it's basically if we have two components, component A and component B, what we need is just um, to multiply accordingly using average. So the mole fraction of uh, A, the mole vapor fraction of A, multiply with the enthalpy of A, and then plus vapor fraction of B, or 1 minus YA, multiply with vapor B. Up to here, is it clear enough? Or do you want to ask questions?
Miss, can you repeat again about the average?
Okay, yeah. The average, if you have a component A and B, like two components, yeah, and then okay. And in here you have a little bit noisy. Wait. I think I'm gonna move. Yeah. Okay. Yeah. If this is still. Wait. Okay, sorry, let's move on to this one. Okay, I think it's better. Right, okay, so if we have component A and B, yeah, if we have component A and B there, so for this, in here, the stream will have a vapor fraction A, right? YA, okay? And what is the vapor fraction of B?
1 minus YA.
Yeah, that's the thing, yeah. Yeah, so the enthalpy average is basically YA multiply with enthalpy of A plus YB multiply with enthalpy B. Yeah, just as simple as that. So as simple as that, and then we just change B with Y minus Y. Okay, so find the average molar and then multiply with the distillate rate and also R plus 1 there, and then you get the Q condenser. Okay, so this is for a total condenser. For partial condenser there, yeah. So partial condenser, I'm gonna write different color maybe. Yeah, for partially boiler, the schematic would be looks like this. This is the liquid going there, and this is the vapor, the distillate, yeah. And then like that, yeah. So the part for partial condenser, the QC would be the distillate, which is the liquid, yeah, the vapor. This one, the vapor multiply with R, the reflux ratio, because this is 1, this is R, yeah, R and 1. So the vapor is actually, yeah, so yeah, the vapor should actually like R plus 1. So this is R plus 1, this is 1, this is R, this is 1, this is R, this is 1, yeah, so the still. So this would be the condenser. And for the partial reboiler, the schematic would be looks like this. So this is the B, and then the partial reboiler would be B. What is VB? I need to check this one, yeah. If we see from the reboiler there, sorry, if you see if from reboiler there, QB would be enthalpy of VB plus B minus this one, yeah. So, but I'm not sure with this formula. Let me check later on, or let us check in the when we do exercise. But anyway, wait. Okay. But anyway, the idea for the Q reboiler is to to find the enthalpy of the V plus enthalpy of B minus enthalpy of L. Yeah. So then would be look like this. Okay. And also there would be there would be like a formula as well from the book. But I think it's better for you to construct your own mass balance and and also energy balance for you. Yeah, I think it's better to construct your mass balance as well as energy balance to get the QR and QC. Yeah. Okay, and later on, if we need saturated steam to heat the reboiler, like in let's say in the heat exchanger, in the kettle's exchanger, the steam rate also can be used by this energy balance. Or if we use cooling water, we can also use like a simple formula, like in the utility system, the system utility. Um, it would be like to get the cooling water rate. Okay, yeah. Up to here, any question? No? Okay, yeah. For the heat duty, I would think that we will have like more exercise. Yeah, maybe we'll Grace next week. We can use previous exam and try to do that, and also try to work on. Can you do that for the time required? Okay. Now, let's move to the next step is what happened if we had side stream. Yeah, what is side stream? Side stream is the the output, yeah, the outlet of the feed of the tray that we may will withdraw. Yeah, if you think about fractionation column for crude oil, you can see that actually there would be like a stream. Yeah, for example, if this is a distillation column, that would be a stream this way, and then this part it become LPG, and this become maybe gasoline and after and diesel, something like this. All of them is called side stream. Yeah, this one is called side stream. What happened if we add side stream? This will affect the mass balance. Mass balance between what? Of course, there would be, and the mass balance will change the value of that will change the value of L, V, L dash, or V dash, or L dash dash, or V dash dash. So it's gonna change the value of liquid or the paper. Yeah, let's say if we draw something like this, if we draw, this is a saturated liquid. Yeah, if we draw saturated liquid from the fractionation column, that means the amount of liquid would be let's say that would be changing, right? So if so, then it's going to change the value. Because L is changing, V is changing. So what happened? It's going to change the slope. Yeah, it's going to change the slope for the operating line. Yeah, if you remember, operating line is basically a slope of L over V. Or for the stripping line, it would be actually L dash over V dash. So that means if you change, if you put a noise there, kalau kita masukkan gangguan, if we withdraw a stream, or if we draw, or we add some more feet, for example, or multiple feet, what happen? It's gonna change the slope. How to calculate the slope? That's what I'm talking last week. We need to calculate the slope. Yeah, we need to calculate the slope, calculate the L and the V, and also calculate the slope, and then draw the slope on the graph to get the real gradient, ya, kemiringan. Now, what happened with multiple feet as well? This multiple feet also similar. Yeah, it gonna affect the mass balance. Yeah, the mass balance here. So if we added something, it would be a changing there. Okay. This one is also the same. So I would explain, for example, this one. Yeah, we have this is an operating line. Okay, this one is operating line, and here there is a side stream. What happened in here? See the key line. This key line suggests what is the phase of the side stream.
Sat liquid.
Yeah, saturated liquid. Yeah, saturated liquid. Okay, then we can again draw a sketch. For example, in the tray. Yeah. First we have L and V, right? We have this operating line. The operating line again is a slope between L and V. Okay, and then we draw the F1. Because it is saturated liquid, what happened is it V the same? What do you think? Is it this one is the same with this? Because they it only withdraw the liquid, yeah, yeah, and then here you will have a new L, which is L minus S1. Okay, yeah, and this one is still V. Now then you will have a new gradient. Yeah, if you see over here, which one is more steep? Mana yang lebih curam? This one or this one? The operating line or the lower one?
The lower one.
The lower one. Yeah, it should be. Yeah, yeah, this is lower one. Okay. Okay, it's because this is L over V. So because V at over V. So you can try to calculate. For example, I have L. Let's say the L is 150. Yeah, and V is, for example, 200. So I have a slope, for example, 3/4, ya, 3/4, 3/4, ya. Jadi so 3 over here, 3 scale, and then 4 over there. 1, 2, 3, 4. Yeah, make a scale. So let's say this is the slope. Yeah. Eh, so yeah, y over v, yeah, sorry, not the slope is not x over y, but delta y over delta x. So let's say the slope would be slope. Yeah, over here. Slope would be, for example, delta y minus delta x equal to equal to 4 over 2. Okay, so when you draw the slope would be 1, 2, 3, 4 there, and 3 maybe in the here. So 1 scale. So in your paper, draw the slope like this. Yeah, this is the slope. Okay, so now and then you withdraw the liquid, yeah. For example, you withdraw the liquid there. So what happened? Let's say you withdraw the side stream is the side stream. Let's say you withdraw 50. Yeah. So your new slope that would be become, so this become, for example, 50. So that would be 20 minus 50. So become 150, 150, or maybe 1 by 1. Yeah. So then the scale would be, looks like this is maybe one scale. So that would be the slope. So the slope is changing from very steep to a bit lower there. Yeah. This one is steeper compared to this one. Yang ini lebih curam dibandingkan yang ini. Ya. Why? Because if you withdraw the feed, if we withdraw the feed, that means your uh, your uh, sorry, I withdraw the liquid ya. Sorry, harusnya tadi no. If I withdraw the liquid, that would be, so the liquid become 100 ya. Yeah, it's correct. Okay, first I have 150 and 20. I withdraw the liquid 50, so the new one would be the liquid is 100, and the V is still 200. Yeah, sorry for that. Okay. I have a problem with this Wacom, so I will use. I'm sorry, I'm just using use the mouse. And this one, so the slope then become L over V. Yeah, L over V. So that would be half. So then you draw 1 point over there. That would be, and two point over there. There, yeah, that would be. It should be looks like, yeah, maybe like that. Okay, yeah, or something like that. Okay, because also from here to here. Okay, now in this point there is a feed. Yeah, in this point there is a feed, for example, and the feed. Let's say, what is the phase of the feed? If it is looks like this.
Partial between.
Yeah, so there would be partial, so it would be vapor and liquid, right? Because it's vapor and liquid, maybe we can add, so the new L dash, let's say, and V dash. We can just try to add, use the mass balance. Let's say the liquid is, maybe for example, we add 50-50 again, yeah? If we add the feed is, let's say it is 100. And maybe, for example, the vapor is 50 and the liquid is 50. So now L become now is 150 and V become 250. Yeah. So then our new slope that would be 3 over 5. Yeah, 3 in the X. 1, 2, 3, 3 scale in the X, and also 5 in the liquid. 1, 2, 3, 4, 5. Yeah. It would be that one, and then you can draw again in here. Then maybe it would be look like this one. And then it is withdrawal, but withdrawal here is it saturated liquid or saturated vapor?
Vapor.
Let's say vapor, yeah. Let's say vapor, and for example, let's say you withdraw 100 kilomole of vapor. So then your new slope become maybe the new one, the vapor is the liquid is still 150, and for example for the vapor it become 150, let's say, because we withdraw 100. This is just an example just to show you how to calculate the gradient, yeah, or the slope. So then it would be again gradient of that one. Okay, so all the changing, always do that based on the amount of vapor and also the amount of liquid. Yeah, but the difference for side stream, the stream is taken out. Yeah, it's drawn, and for multiple stream, the feed is put inside in the mass balance. Yeah, so this is for the side stream, and this one is the multiple feed. Yeah. For example, you have this line here, and then you add one feed number one there, yeah, over here. And then what happened is the liquid would be much higher, for example, because this is saturated liquid. Yeah, so just think that see the Q line, and this is the saturated liquid. Yeah, and because of saturated liquid, that would be over here L is more than L, yeah, L dash more than L, and V is the same, yeah, V equal to the same. So that means the slope L over V would be a little bit more steeper, yeah, jadi lebih tinggi slope-nya. That's why it would be looks like this. And this one, we also add another one, let's say vapor and liquid. So this one is vapor liquid, yeah. Vapor and liquid, for example, half, yeah, 50% vapor and 50% liquid. And then you just add the liquid to the liquid and the vapor to the vapor from the feed, and then you can get your new slope. Yeah. So basically, this one is the typical of multiple feed. This type of question, it may be asked in the question number 2 about the additional assessment. Yeah. So for example, what happened if we add multiple feed? Yeah. What happened to the equilibrium stage, for example, or what happened if we add a if we add side stream, we put side stream to withdraw some of the product? What happened to the quality of the bottom, for example? Yeah, or if the tray is the same. Yeah, so this is a typical of question question in the problem solving. Okay, now okay, I think I'm gonna ask let's see if we have question before. This one. Oops. This one. Yeah. For example, this is a typical the equilibrium diagram. Yeah. Um, so typical question in the problem solving would be, for example, let's say I want to to put side stream when x equal to 0.3, for example, this one in a liquid form, yeah, in saturated liquid. What happened to the column? If the bottom product will have similar, for example, if it will have similar composition, or what? What is the implication if I add side stream there? Can you guess?
Different, ma'am.
Hmm? Yeah.
Different, ma'am.
Yeah. Why is different? You need to answer that with some reason.
Because like in the gradients, there are change in liquid and vapor composition.
Yeah. That's the thing. So let me add one slide, yeah, so I can discuss this one. Let's add a picture. Now, usually, you will have two type of questions. There, make it bigger. Okay, let's say I have this question. My question is, if I do a side stream at x a equal to 0.3, what will happen to the quality of bottom product? Yeah, so good. Okay. Uh, who answered before?
I do, ma'am.
Okay, Rosemary. Good. Then of course going to be changing, yeah. So what happened to the quality of the product? For example, for this case, the tower is there. The tower is there, so you can't really change the tower, right? But if you change the tower, then it would be you have to just refabricate again the distillation tower. So then you have, let's say, you have 7 tray. Yeah, because one tray is for a partial reboiler. So what will happen to the quality of the bottom product if we use side stream? First, we need to find that side stream at 0.3, this one there, okay? And then we need also know the phase, yeah? We also need to know the phase of yeah, the phase the phase of the of the side stream. For example, in my case, the side stream, it should be, I want to get withdraw the saturated liquid. Yeah. So here, so saturated liquid would be, where's the key line?
Straight, ma'am.
Yeah, straight, vertical, yeah, vertical. Okay. So you can imagine, this is, you have L over V. How you determine L over V? That's a good question. To determine L over V, you have to construct them from mass balance, yeah? So that means you have to, it's a little bit work, yeah? You have to construct them from the mass balance between the B, this is D, this is L, This is V, yeah. Construct from the mass balance from the feed, yeah, from this one. So you should know the value of L and V, yeah. Once you know the value of L and V, and also find the mass balance as well in L dash and V dash for the stripping. Also again based on the mass balance, mass balance of each envelope in every envelope. So once you know your L and V, and you know the how many saturated liquid that is withdrawn, and then you can calculate the new L dash dash and L and V dash dash. Yeah, it's gonna be a little bit of work because you need to calculate the value of D F, of course, D L V, and then find the L over V. You with some yeah, with some the you can get the L from D, right, from the vapor fraction. And how you get the V? You do get the phi from the slope. Yeah. So once you know the L, you can get the operating line here. Calculate by measuring very good with your ruler, and then find the slope. When you get the slope, find the slope, you can get your V. Okay. And then put uh, the this one, which is the mass balance on the feed area there, the feed one. So there is a feed, there is L and the V. You calculate it from the slope there. And then you know also the feed, for example, is all saturated liquid. So it would be, this would be, L dash would be the liquid, FL minus the all the feed, yeah, in the feed, because it's saturated liquid. So you can find the L, and you also can find the V dash from the slope of operating line there, the stripping line. So it's all basically all about to calculate the mass balance there. Once you know, calculate this one, and then you can maybe, for example, okay, I want to withdraw side stream, for example, 50 kilomole, and then you can withdraw from the liquid there, so you can get a new slope, yeah, nanti bisa ganti the slope. And once you know the new slope, then you can draw your new slope from here. Maybe, what is your guessing? Is it gonna be, what is your guessing, yeah? Is it gonna be, let's see, Shan. Is it gonna be looks like from here, yeah? Is it gonna be looks like that, or is it gonna be looks like this? Which one? This is it gonna be the blue one, or is it gonna be the change it? Is it gonna be the red one? What do you think about the slope?
I think it's the red one, ma'am.
The red one. Why?
Because the side stream is saturated liquid, right?
Yeah,
Yeah. So the slope will be steeper.
because the slope is this one, right?
Yeah.
This one is lower than this one or higher?
Higher.
Side stream. You taken out the liquid.
Wait. Uh,
Would be lower, right?
yeah. If we
Yeah,
take
yeah,
away, then the blue line.
yeah. So that's what I'm thinking. So, for example, it would be looks like this. Let's say, yeah, because it is steeper. Because you withdraw the liquid, yeah, the saturated liquid, and then this one should be maybe a little bit lower, right? Yeah. And then let's say the scale is the same, so it would be lambda, yeah. Let's say. So that would be the one. But the idea is the same. So with this case, let's say I calculate and it's gonna be this one. So how about the quality of the bottom product? If I want to ask quality of the bottom product, that would be okay. This is 1, 2, 3, 4, 5. For the sixth one, you will have a new stripping line, yeah. 5, 6, 7, 7, 8. Nah, because we only have 8 tray, yeah. So this is your new product, new end product. So how about the quality of the new product compared to this one, to the black one? I would say the quality of the product would be the XA would be higher compared to the original one. Yeah, let's say if the XA before there's a side stream, maybe here is about uh, 0.7 for the bottom product. Yeah. Now, because of the side stream, maybe the A would be, sorry, not 0.17, 0.0, ini 01 ya, 07 ya. Yeah. It becomes 0.1. So the remaining A in the bottom product is going to be higher compared to the original one. Okay. Yeah. Do you have any, do you want to have a discussion or any questions?
Ma'am,
Yeah.
I want to ask, so the purity of B will be lower, right? If we
No. The purity of A in the bottom.
okay, so the fraction of the B is lower.
Higher. B. Oh, the fraction in the bottom, you mean?
Yeah,
Yeah,
in the
yeah.
bottom.
Yeah.
Would be lower. Would be higher, the blue one. Kan 0,1.
B. Winning.
Oh, the B. Yeah. The B is lower.
Yeah, if the so we get more fraction of A, so the B will be lower. And I want to ask, why do we use side stream if the purity we don't get we get lower purity? Why
Oh,
would we
yeah.
use side stream?
Here's the things. The product that we want is in the distillate. Yeah. Kayak ya. So the product that we want, hello?
Maybe she asked because we are
Sorry ya.
dealing with a binary and they will meet this one, but for binary they
Okay.
not get this one.
Why you do the size stream? Okay, Ataya. Here's I think Ataya asked ya. Okay, here's the thing. The product that we want is not the bottom product, but distillate. Yeah. So the product that we want is actually is in here. Distillate. Yeah, this one. Nggak enakan ini. Yeah. This is the product that usually we want to sell. Yeah. I want 95% purity of ethanol. I want 95. So this is the main product. But why you use side stream? Because sometimes you want to have a particular composition that is similar to the side stream. Yeah. For example, forever for this application, we want a product with 0.3, for example. Or rather than making a new column to make 0.3 for the product, why don't we just take them out from the distillation column? Yeah. So the quality of the bottom product is actually doesn't really affect. It's gonna affect the recovery, the overall recovery if we calculate the mass balance. But this is actually not the product we want. Yeah. If you think about it, think about fractionation column of the crude oil. Yeah, first you want the product, the LPG, the natural LPG, for example. Oh, there is a side stream. There is a composition in the distillation column similar to gasoline. I want that. I want that because we need the C6, yeah, C6 to C9, the naphtha, for example. Then we do side stream. Okay. Oh, and then there's a diesel in the composition, and then we can add it. So the bottom product actually just how many remaining material that we want left. So, for example, in the crude oil, the bottom product is the asphalt, yeah, a bitumen, like something like that. So the XA, the product we want should be very lower, yeah. But this case implied that if you calculate, if you want to have, let's say, um, uh, the distillate in here, and then you want to add side stream at 0.3 because it is saleable, it can be sold, for example, the remaining one will have still purity of A is higher, yeah. So we're just gonna talk about the purity of A, yeah, something like that. So, what happen if I want to just make B, ya? Saya pengen komponen yang B gitu ya. I just want to the component B. Usually, we gonna use in the multi-component distillation. Usually, we will add another tower, yeah, another tower, another distillation column where B is gonna be the the product, and then you can get the pure B. Is it answering your question? Hello?
Yes, ma'am. Thank you.
Yeah, okay.
Yes, ma'am.
Yeah. Okay. What happens if you add multiple feed, for example? That is also sometimes we want to inject, and maybe for the multiple feed, sometimes maybe we have the spec, but the spec is changing with the previous one, for example, and we can add this one. Yeah. So this is gonna be like a more or less typical in the problem solving in number 2. So you need to be able to answer but with calculation, yeah. So usually that's why you have to finish the first one. You have to finish the design of the distillation stage first, for example, and then so you have the baseline for the calculation, and after that maybe there's some question. For example, what happens if we change the feed, yeah? Yeah, you can answer that. I have one question again. What happens if we change the feed into 50% vapor and 50% liquid? Yeah, for example, we have new feedstock, and what happens if the feed is changing into 50%? 50%. Enggak enak nyanyi. Anyone want to try to ask?
What happened to the key line?
Right, make a Bu Grace. Make new key line, yeah? Let's make a new key line. So I would try my best to find the key line. So this is vertical, horizontal, so would be like that. Yeah, it's there. Oh, in the point there, over here. There. Then what happened?
What happened to the steps? And
Any idea? If you change the feed, then the point, the intersection point between the Q line and the enriching is gonna changing as well, isn't it? Yeah, let's draw a new one then, so I can okay, easier, yeah. So another. Okay. This one. What happened if we change the feed, yeah? Oh, tahun 12 already. Oh, 12 already.
Yeah, it's gonna be okay for winning because this also part of our assignment.
Good guys, can you?
Sorry.
Maybe don't use your ini ya. Don't use your headphone maybe because it's like like. I think it's better if you don't use headphone. Okay. Anyway, what happened if I one more? Yeah, very quick. What happened if I change the feed into 50% vapor and 50% liquid? So we will have new key line, yeah, maybe around here. Okay, so that means what we can see is that actually the cross section points between the enriching and the Q line is shifting, right? And because of that, we're gonna it's gonna have a shifting uh, with the Q with the XB. So that means there would be 1, 2, 3, 4, and then if because it's shifting, so we need to find new key line. How we we will need to find the stripping operating line. How we gonna use stripping line? How are we gonna find the stripping line? Stripping line is L over V, yeah? Now, because we need to find L and V there, and we get the add of the feed there, because if we change in the feed, so that means maybe for example half and half. So then once you know the L and V, and F is changing, then you need to find new LV and LNV dash. Okay, if in the design section, if you haven't made the distillation column, maybe you can design again your distillation column, and for example there, yeah, make a new new operating line, and then 1, 2, 3, 4, 5, 6, 6, 7, 8, 9. So basically, if this is a design question, if it is a design question, you haven't made the distillation, kalian belum buat kolom distilasi, masih berupa design, then if you want to have an optimal one, XD over here and XD over here, you need addition 9 ya. 1, 5, for example, 5, 6, 7, 8, 9. Yang baru jadi 9. Jadi the new equilibrium stage now become 9 stage. Okay. However, if it is a problem solving case, then you can use this one. Yeah, you can you need to use, you need to calculate first what is the L and V, L and V and the feed, and if the feed is changing, then you need to calculate L dash and V dash, and then find the slope. Once you find the slope, and then you calculate up to 8 tray, because you only have 8 trays, and then you can check about the XB. Is your XB is the same, or is XB is changing? Okay. All right. So we can discuss this one later on. Sorry, not subtitle there. But however, screen. Let's see the summary then. So anyway, I just want to sum up for the theory. So we actually can separate distillation, a binary mixture using the distillation, provided it should have quite high relative volatility. In the this one in the rule of thumb is about greater than 0.5. And distillation is the most and mature and widely used separation operation. And also the design procedure, the operation practice are well established around the world. And also the technology also established. And the purity of the product would be depend on the number of equilibrium stages on the enriching section, rectifying section, above the feed entry, with the stripping as well, yeah, below the feed entry, and also the reflux ratio that we calculate. So this will it will change the purity of the product. Also, it depends with equilibrium stage as well. And then the common conducted would be like in tray, yeah, seperti apa? Ya, look in a tray, or like sieve tray, and distillation also equipped with condenser at the top and the cooling water, and also reflux, reboiler, and sometimes heat it with a steam, the easiest one. Why you don't use fire? Because fire is too much. Yeah, fire. The temperature of fire is like 400. 500 degrees Celsius, you don't need that high of, otherwise your component is going to be just burned, especially for hydrocarbon. So how to put the heat is just to use the steam through the reboiler. And McCarthy method is a method to determine the stage and reflux requirement. We assume that a constant mole overflow is valid. Okay, this is a quiz. Not quiz, let's start 2 minutes. A mixture of methane and ethane to be separated by distillation. Explain why water cannot be used as a coolant in the condenser. Why we can't use water as the coolant in the condenser? First, think about the temperature of the methane. Yeah, if you can read closely, methane and ethane, the boiling point and the boiling point is much lower than 0, right? Should be in minus. So that's why we can't use water with the temperature of 25 degree as the coolant and condenser. When we need a lot like refrigerant as the condenser. Yeah. So mixture of methane and ethane is actually separated by cryogenic distillation. It is happening cryogenics. The second one, why there is an economic trade-off exists between number of trays and reflux ratio. I think number 2, you should be able to answer this, because if you increase the number of trays, then you can lower the reflux ratio, which is lower the operating cost, but you're gonna increase the capital cost. Or but if you lower the number of trade, then you have to increase the reflux ratio, or to increase the operating cost, yeah, for heating up the reboiler, to cool it down with the condenser. It's gonna be really, and also the pump, yeah, so the pump, and then that's why you need it's economic trade-off. All right. I think that's all. I'm gonna give this to Bu Grace.
And wait a minute. Let me present. Okay, so last time you have this one as your assignment, right?
Yes.
Everyone can hear me, right?
Yes.
Okay, so you have a binary mixture of A and where A is more volatile than B, the more volatile component to draw the XY diagram. And you are given the XY diagram, but most of you did not use the graph I have given to you previously. So some of you only write down your answer on the answer sheet, and I just copy the number. For that, it's okay. I will check the number, but it is better for you to use the tools given to you to complete the exercise. Okay, so here the uh, the feed is saturated liquid, right? Saturated liquid feed. And with the composition is known of 40% A and 60% mol B. Then we can get the Q line from this data, right? You have this, I think there is in the module, you can find it out. So the Q line for a saturated vapor is number 1. It is going downstairs. Why? Anyone knows? Anyone? Because the M will be, the gradient will be what? Can anyone answer me? Please give me some feedback. Sorry.
Ma'am, can I
Please,
try to?
sorry. Oh, okay. I'm using two computer because my computer is too loud. The sound is not good. But yeah, sure, you can answer.
The gradient will be negative.
Sure, the gradient will be negative. That's why we get this one over here, right? Sorry, it is not this one, but this one. My finger is not that good to draw a line. Okay, and if you got the saturated vapor, you will get the straight horizontal line. Why? Because, anyone can answer?
The gradient is 0.
The gradient is 0 is 1 point, and the other one, you want to intersect dy, right? Dy axis. You want to intersect the y-axis because all are vapor, right? For the liquid, it should be parallel with the y, or you want to intersect the x-axis, right? We all know, right?
Yes, ma'am.
Okay, so everyone now get why the key line goes that way.
Yes.
Okay, anyone has a problem on determining the key line? No? Okay, we can get through. Okay, and then we are expecting a product of distillate containing 90% of A and the bottom product containing of 10% of A, right? And you have to seek the reflux minimum, the number of reflux minimum. And the B1 is determining how many stages of equilibrium stages are needed to obtain the product, right? Okay, so most of you, I think, already got the point of designing the distillation column. So at first you must what? Put the distillate and the bottom product, or put the feed. Okay, according to the question, we must put the feed first, okay, because we know the feed earlier than the bottom and distillate product. Then if you got another type of question, just read through the question and start to draw on your paper, right? Okay, then you got the distillate composition of 90% A, and the bottom product composition of 10% of A, right? Then you need to determine the reflux minimum, right?
Yes, ma'am.
Please come with me. I mean, please join me in completing this exercise. Okay, so for the operating line of the enriching, you have to intersect the key line with the equilibrium line, right? And you got this point right over here. And then draw a line to that intercept minimum. The intercept minimum of 0.41. When you put it into the equation over here, this equation, you got the air minimum of 1.14. Up to here, anyone has question? No? Let's continue. Then we are going to determine the reflux, right? The reflux. Calculate from the question that the reflux should be 1.5 from the reflux minimum. And the number you can calculate is 1.71. Once you put it into the equation, you got the I is 0.33. And you draw the corrected operation line for the enriching. Up to here, anyone have questions? No? Then let's continue. After getting the enriching operation line, then what you need to know?
There's
Please
how many
answer me.
stages?
Yeah, how many stages? Then what should you do to know how many stages is there?
Take a straight line from XD.
Correct. Draw an operation line of the stripping, of the stripper, right? From XB to the intersect between all the lines, feed and the enriching line over there, right? Okay. Bu Winnie already explained to you how the gradient is very important. Once you take something or add something to the system, the operation line will be changing, but the equilibrium line is still always there. It never changes. It only depends on the component, right? Anyone get that?
Sorry, Miss.
Understand?
Can you repeat again, Miss?
Okay. The operation line can be changed. Yeah. If you add some stream into your system, or you uh, take off something from your system, it will change the operating line, but never the equilibrium lines. Okay, bear in mind about that. Any objection? No? Okay, let's
No.
continue. Okay, let's continue. So after this, you already get the operation lines for both stripping and enriching. Yeah? And you know where the feed enter the system, but you don't know where the feed enter the stages in your column. So you start to draw a steps, right? Okay, drawing a steps right there. And we find that the feed enters straight right at the step number 4. As Sabu Winnie already told you at the beginning of the class. Yeah. So they're right there, right over there. I mean, the feed enter the column right over the step number 4. The equilibrium state, equilibrium step of the fourth equilibrium. Okay, and then you can calculate how many steps is there. Some of you get 9, some of you get 8, some of you get 10. It's okay, but never more than 12. Yeah, I saw some of you, one of you answered 12. Maybe you are not drawing well. So if you are using a ruler and you draw in line with the tools given to you, I think you are going to have 9 or 10 or 8 steps. Okay. And I'm not saying anything about the reboiler. I'm not saying anything about the condenser. So you can answer it accordingly. Yeah, if you know the reboiler is partial, then you need to deduct it with 1. If you know the condenser also partial, then you need to deduct it with 2 steps, just like that. Okay, so once I calculate, I found out that the stages is 9.3. If there is a point over there, you need to put the point, put the significant number over here. Yeah. Usually it's only one significant number, two significant number, I mean, one after the point. Yeah. Okay, up to here, any question?
Ma'am, I would like to ask.
Yeah, sure.
Okay, I will ask. I have 2 points that I don't understand. Is that how do we determine the Q line gradient, and how do we determine the intersect point between the Q line and the line from the XD to the y-axis?
Okay, so for the beginning, I answered the key line first, yeah? So the key line, key is what? Key is equal to liquid over paper. Am I right? Of your feed, right?
Yes, ma'am.
The composition of key is the fraction of the liquid in your feed, right? So key is L over P. Once you get the saturated liquid, then the key will be 1 over 0, right? Okay, so saturated liquid will give you the vertical line over there, right? Because you got the Q is what? Unlimited. Yeah. Okay. So if you have Q is saturated vapor, how about that? 0 per 1 is equal to
0.
1. 0. Sorry.
0.
0. Then the gradient, because the gradient is Q. Oh, sorry. Ah, okay. Let's just leave it there. The gradient of Q line. Can you get the gradient of Q line? The gradient of Q line is Q per Q minus 1, right? So it should be 0, right? Then you got that saturated vapor fit, the Q line for saturated vapor. Once you get the equilibrium of vapor and liquid, it will be in the middle of these two lines, right? And you need to calculate that M. M equal to, sorry, Q per Q. I will not go with derivative, yeah, because Bu Winnie already give you the derivative equation. You need to calculate this one, right? From QL per V of the pit, and then the M you can get from the key per key minus 1. That's how you determine that Q. And as you know, the Q is usually be determining at the beginning. If you got any information about the feed, you need to put it right at the beginning before you start everything. You see? Understand?
Yes, ma'am.
Okay. And then to get the reflux minimum, the reflux minimum is where the equilibrium lines and the Q lines intersect with one another. And then you start to intersect that point to the XD. So the intersect of three lines here. The equilibrium line, the key line of the Z, the feed, and then the distillate enriching lines. Okay? Then you get the intercept minimum. Am I answering your question?
Yes, ma'am. But what if the I see like in
The
some
Q
questions.
is here, over here. Then how about the reflux minimum? It should be taking this point and then make a line straight to intersect the point, right? I'm not good at drawing lines. Okay, okay lah. Yeah, you got the point, right? Then you just draw the line straight through to that point. And this one will become your intercept minimum or reflux minimum can be calculated from. Up to here, am I answering your question?
Yes, mom. But what if like in some questions they ask they put the intersection point between the Q line and the enriching point is like 1:3. So it's not like it's not like that. So
Yeah,
it's
of
like in the
course.
middle.
You can if the Q is not 1/1, you mean that the Q the liquid is not equal to vapor. You mean that?
Yes.
Okay. If the Q if the L is twice the vapor, 2.1, then you need to calculate the gradient, right? Sorry, wait a minute. Mommy, wait a minute ya. Okay, let's continue. You can calculate the gradient. The gradient is Q over it will uh, move towards the vapor, the saturated vapor, right? Because the vapor is more. So you got the line over there, 2 and 1, 2 and 1. So you got the vapor over here. Get that? So the key line will depend on the composition of liquid and vapor in your feed. After you got the key line, then intersect the key line with the equilibrium line. The equilibrium I know, but this one. Sorry. Yeah. So am I answering your questions?
Yes, ma'am, you're answering the question.
Okay. Any other question still haven't answered yet?
Ma'am, I want to ask.
Okay, that's how you determine the R minimum ya. R minimum is the intersect between the enriching line with the feed Q line and also the equilibrium line. So the intersect between three lines. Okay, and start from that, you can determine the reflux, operating reflux, and then you can determine the stripping line, operating line, and then you can go on with the steps.
Ma'am,
Yeah.
Can I ask how to estimate the like 9.3 like that, ma'am? Or is that any tolerable errors for that, ma'am?
Yeah, we have that tolerable. I mean, we will tolerate your error. If we see here the scale is 5, 0.2 to 5, so one scale is 0.04, then you calculate maybe miss a little bit, we will tolerate that. But we do need to understand that you know the scale and how to use it.
Okay, ma'am.
Okay. So everyone with the answer 8, 9, and 10 are all correct. Yeah, for this question, very question. For me, I'm getting the 9.3 because I see that my XP is 1/3 of these steps. So that's why what I can say that the stages needed is 9.3. If you go with the half, it's okay, 9.5. If you right at the end of the 9 steps, is also okay. Then you can put 9.0 or only 9 steps is okay. But if you know that there is more than 9 steps needed, you need to put the significant number, one significant number over the point. Okay, as a decimal, I mean. Okay. Any other question?
Miss,
Yeah.
we can know the ratio of L of liquid and vapor based on the feed condition, right?
Yeah, correct. It will be given.
Okay.
Yeah, it usually will be given. But if you are not given that information, you might be given the reflux. The actual reflux might be given. And from the actual reflux, you can find where the feed enters your column. Yeah.
And from the actual reflux, we must find the minimum reflux.
Not, no, it will depends on the question. If
Oh,
you are asked of the minimum reflux for this kind of graph, you will be given the information of the feed, the composition of liquid and vapor in the feed, usually, yeah.
oh,
But if you have another kind of uh, another kind of material, I mean, of the compound, where you find out that the equilibrium line is not just an arc like this, it might be it might be uh, like this. Sorry, should be from here. Yeah, might be like this, or sorry, let's just end this one and discard everything, and I will. Oh, sorry. If you have another kind of Bu ini, we still have time
11 already.
already.
Yeah, 11 o'clock.
Okay, okay. If you have another equilibrium line like this one, fat on the top, fatter on the top, or slimmer on the top, like this. Phew.
That's
Yeah.
fine.
Sorry, I do not have the pen. It's
Yeah, I know.
frustrating
Yeah,
drawing without the
yeah,
pen.
yeah. It is struggling to teach separation process online, yeah.
Yeah,
We usually use Blackboard.
yeah, blackboard and whiteboard. Okay, so if you have the fat on the top, like this one, then the reflux minimum will depends on the stripping law. But if you have the slim bottom, sorry, slim top, slimmer, this one. Ah, yeah, maybe I will prepare some for next week for you to exercise, yeah. But
Yeah.
you know that the at least you know that the equilibrium lines is not always symmetrical arc like this. It can be fat on the bottom or it can be fat on the top. Okay.
Yeah.
Later on, we will discuss about that. How to determine the reflux minimum from the equilibrium lines. Okay.
Yeah.
okay.
All right, thank you, Bu Grace, for your explanation. So I think next week, Bu Grace, I think it would be good if we can have an exercise, yeah, like
Yeah,
exam
sure.
year or last 2 years, and we can give the exam on Thursday, and let you try it first, and then we can discuss on Friday. I think that would be useful. Yeah. All right, everyone. Thanks for listening. Um, if you still can digest the idea now, let's try to exercise on Thursday, and we still have one more week to really cover the material about the distillation. Okay, then I'm gonna end the session, and thank you for attention. Yeah.
Thank you, ma'am.
Thank you, ma'am.
You, ma'am.
Thank you, ma'am.